Hello, I'm Jan, and in this video I'll describe to you our paper named Distributed Graph Problems through an Automata Theoretic Lens. This is a joint work with Iram Chang and Duka Somel. Let me start by giving you a high-level picture of what we are trying to solve. We are given a graph problem pi, and our goal is to design an efficient algorithm that will answer the following three questions. First, is pi solvable for any graph? Second, can pi be solved efficiently? And third, what is an optimal algorithm solving graph problem pi? Of course, this is a very broadly posed question, so in our paper we study the following special case. The graph problems that we focus on are locally checkable labeling problems. Such problems are, for example, computing coloring of a graph, finding consistent orientation, or maximum matching. Moreover, we require that the graphs where we want to solve such problems are only unlabeled paths and cycles. These graphs can be either directed or undirected. The reason for this restriction will be explained soon. On the output side, we give the answers for the local model of distributed computing. In this model, the input graph describes also a communication network. Each node has a unique identifier of an order of log n bits, and in each step, nodes can exchange arbitrary long messages with their neighbors. The key measure in this model is the round complexity. Round complexity measures the number of rounds required until every node has finished exchanging messages. Hence, lower the complexity, the more efficient the algorithm is. Now, as I have defined the setting, I can describe why we have picked cycles and paths. From the prior work, we know that in the local model, problems on cycles and paths are either constant round solvable, log star solvable, or global. But the proofs establishing this classification do not give us any algorithm how to classify a specific problem. So it is a very natural research direction to see how efficiently can we do it. As a first step, Brandt et al. Showed that in the case of unlabeled directed cycles, we get a simple characterization. But in the same paper, they also show that already in the case of 2D grids, efficient classification is impossible. In fact, it is undecidable to determine a round complexity of a given LCL problem. Recently, Baliu et al. Showed that the same question is already p-space hard for labeled paths. So it is unknown whether it is possible to efficiently classify problems on cycles or paths, or whether it's already hard. Moving on to results, let me tell you what have we obtained. Most importantly, we give an affirmative answer and show that indeed, almost all questions on cycles and paths can be answered by a polynomial time algorithm. Such algorithm answers: first, solvability of a problem pi in all except one case. For such case, we prove an NP hardness result. Next, it gives the round complexity of pi without any exceptions. And finally, we give a way how to construct an optimal algorithm for solving pi. The way how we have obtained the results is by designing an uniform automata theoretic formalism for the LCL problem. In the rest of the talk, I'll explain to you how to see an LCL problem as an automaton, and afterwards how does it characterize the LCL. So, how to see an LCL problem as an automaton? First, I need to briefly explain you the LCL formalism. For representing the LCL problems, we chose node edge checkable formalism, which was introduced by Baliu et al. In 2020. In such formalism, we imagine that each edge is split into two halves, and the task is to label the half edges according to some constraints. To illustrate the formalism, I have picked two LCL problems. I chose edge coloring on the left and consistent orientation on the right. They will be our running examples for the whole talk. The constraints that define an LCL problem are divided into node and edge constraints. The node constraint represents allowed labels next to any node. Hence, for free coloring, it will be every combination of different colors. Similarly, the edge constraint represents allowed labels for the whole edge. Hence, we see that the edge-free coloring has only 1, 1, 2, 2, and 3, 3. For the consistent orientation, we have two labels, H as head and tail as t, and from the constraints we see that they need to keep alternating. As we are considering only cycles and paths, the constraints are just pairs of allowed labels for both node and edge constraints. To summarize, an LCL problem is described by the node and edge constraints, and such formalism is as expressive as classical definition given by Nauer and Stockmeyer. The next step is to turn such description into an automaton. In our case, it will be a non-deterministic automaton over unary alphabet. How does it look like? The connection is very natural given the formalism I have just explained. We identify the states of an automaton with an edge constraints and transition with the node constraints. Again, let me explain it on the examples. The automaton for the edge coloring will have just 3 states. These states will be 1, 1, 2, 2, and 3, 3. For the transitions, they are between any 2 states. But because it has to be a free coloring, it doesn't have a self loop. In the case of consistent orientation, we'll have just 2 states, and these states will have a self loop. To summarize, by the above procedure, we can see any LCL problem as an automaton. Next, I'll show you how to use this automaton to characterize the LCL problems. It will be a 3-step process. As a first step, we classify each state of an automaton into one of the 6 types. I'll now describe the first 3 types. First, a repeatable state is a state to which we can return. Second, a flexible state is a state to which we can return in exactly k steps for any big enough k. And third, a loop state is a state which has a loop. For the next 2 types, I need the definition of a mirror. Mirror of a state is just a state with flipped label pairs. For example, a mirror of a state 1, 2 is 2, 1. Now, for the types, a mirror flexible state strengthens the flexible state to moreover reach its mirror in exactly k steps. And the mirror flexible loop just combines the loop and mirror flexible type together. Again, let me go over our 2 running examples. Let's look at the case of 3 coloring and, for example, pick state 1, 1. To this state, we can return in 2 steps by e.g. node 2, 2, and also 3 steps by using both nodes. And by combining these returning blocks, we can return to 1, 1 in any number of steps, so such state is flexible. In this case, it is also trivially mirror flexible. For consistent orientation, each state has a self-loop, so it is a loop state. But as they cannot reach themselves, they are not mirror flexible loops. In the paper, we show that all such types can be computed in polynomial time. Non-trivial cases are the flexible types. As a second step, we determine the type of an automaton based on which states it has. To have a full characterization, we need 13 types. These types fully determine solvability and round complexity, which will be shown on the next slide. I'll not go over the whole table, but only explain how to classify the free coloring and the consistent orientation. For the free coloring, it has a mirror flexible state, but not a mirror flexible loop. Hence it will be type E. For the consistent orientation, it has a loop, but not a mirror flexible loop, hence it will be type C. And now, finally, we have everything needed to answer the solvability and Brown complexity. The free coloring is of type E, so it will be log-star solvable in both directed and undirected case. For the consistent orientation and any type C problem, it is trivial in the directed case, but requires n rounds in undirected case. Interestingly, from such characterization, we also obtain the converse. That is, any log-star solvable LCL problem in undirected case has to have a mirror flexible state, and the constant time solvable problem in an undirected case has to have a mirror flexible loop. Before conclusion, let me quickly describe you one more observation that allows to transfer some of our results to rooted trees. The extension to rooted trees works only for so-called edge-checkable LCL problems. In this class of problems, we are labeling nodes, and the constraints needs to be checked only along each edge. An example of such problem is a graph coloring. For such problems, we show that with some minor modification, we can translate a distributed algorithm from oriented paths to work also on rooted trees. Hence, the classification and the algorithm synthesis is the same as for oriented paths. Now we proceed to an end, so let me summarize the talk and our paper. The task was to design an efficient algorithm for characterizing the LCL problems. We showed that it is indeed possible in the case of cycles and paths. The key technique was to represent LCLs as automata. Given such automaton, we can easily answer solvability and learn complexity. In the full version, you can find how to synthesize an optimal algorithm using automata, the connections with directing words, and also all the proofs that were omitted in this talk. If you want to try out the classification, just go to lcl-classifier.cs.auto.fi and find out round complexity of any problem you want. I'll be happy to answer all questions during the Sirocco session. Bye.